So first off, what's a polymer? And there's a couple of different ways to look at this schematically. One way we like to do it is just to think of a polymer as a chain, right? A polymer is a chain of monomers. A monomer is a small molecule. There are many options for monomers. We're going to be seeing a number of them within this chapter. And I just want you to know that a polymer is lining up and chaining up a whole bunch of those small molecules. So if we look on the right here, A represents a monomer. B represents a polymer, right? It's a chain of many, many monomers. C represents what we call a copolymer. And that's just a polymer of 2+ monomers. So copolymers just have more than one monomer in them. It doesn't have to be regular like this. It doesn't have to be square then circle, square then circle. It could be square, circle, circle, square. It could be any sort of random arrangement of them. But a copolymer just means there's more than one monomer involved. So a polymer is just a chain of a bunch of little small molecules. They're chemically bonded together. There are a number of natural polymers that you're familiar with, whether you know them by name or not. Let's start in this upper left-hand corner here. Rubber, or polyisoprene, is a natural polymer. Polyisoprene you can actually sort of tap out of trees in a similar way to how you tap maple sugar and maple syrup out of trees in the spring, for example, the early spring or late winter. If we go to the upper right-hand corner, cellulose, which is what cotton is made up of 90%, is a polysaccharide. You can see that there's a monomer unit here, and you see how it just keeps coming back over and over and over. This N just means a whole bunch of them chained together. Same thing with the polyisoprene, right? You see how there are units, and those units keep repeating out into infinity. N just means lots and lots and lots of them chained together. What about pectin? If you've eaten jelly, you know something about pectin, and pectin is a polymer of what's called polygalacturonic acid. And if we take a look at pectin, here's my repeating unit over and over and over, right? This is a monomer. This is a monomer. Another monomer here, right? These are all natural polymers. That N, that number of repeating units, could be anything. And in fact, the number of repeating units in the polymer, the size of that N, the magnitude of that N, does sometimes govern the properties of the polymer. Polymers that have more N, that have longer chains, act differently than polymers with shorter chains, for example. But the big thing that all polymers have in common is they're what we call macromolecules, right? Macro, if you think to that root word, just means big. If you have thought to your gen ed courses here at Manchester, you might have taken macroeconomics, right? That's the economics of bigger systems, is it not? Polymers are macromolecules. They're huge molecules. That's all that a macromolecule is, a big molecule. They involve thousands of atoms, right? Macromolecules have thousands of atoms in them, and their molecular masses can be over 1 million. So 1 million grams per mole or 1 million AMU. Millions of atoms in macromolecules, thousands of atoms in macromolecules, and they get very big. Let's take a look at some different synthetic polymers. What I would like to look at for this point is polyethylene. So polyethylene, right? We know that it's a polymer. That's what the poly means. And the monomer must be ethylene. That's what polyethylene means. And so I've got a little animation here from your chapter. Let's go ahead and build ethylene very quickly, right? Ethylene is C2H4. And if we build ethylene, I'm just going to start dragging hydrogen atoms, right? We've got 2 carbons here and we've got the hydrogens, and as we drag them over, it's just going to start forming chemical bonds. So this is the ethylene molecule. Another way of drawing it is a carbon with double bonds and 4 hydrogens on the outside, right? C2H4 is ethylene. Alright, so I told you that we had the ethylene monomer. Remember, the ethylene monomer looked like this. It's a single carbon, it's a double bond between 2 carbons, so 1 carbon double bond, and the chemical formula is C2H4. This is all about the monomer. Let's see how polyethylene forms, right? What you need is some sort of initiator, right? And that initiator is what we call R dot. So that's our initiator. This is what's called addition polymerization, which means that I have to come up with some way to string all of these ethylene molecules together like train cars on a boxcar. So let's take a look at this R and see what happens. We're going to initiate the addition polymerization. What R does is it makes the bonds in the molecule rearrange. See how it took away one of those single bonds in ethylene? And now what it did was it hooked itself onto one end of the ethylene molecule, and there's this leftover electron in ethylene, and that's from the double bond. And that leftover electron is going to go after another ethylene molecule. I'm going to drag that in here, and let's let it go after it and see what happens. There we go. It went after the ethylene, it took away the double bond from the monomer, and now we've got another single bond. Let's let it go after another one. And so on and so forth. You notice that what is always left is one of these nice little dots, these radicals. And the way that this would end up is you either run out of ethylene molecules or you kick into another R molecule later, right? It kicks into the initiator. And so what you end up with is R, C, 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 R, and there's H's all along. Let's make this look like a real molecule, huh? Right? That's what we're looking for. You get a very long molecule, and the R's cap either end. Addition polymerization always ends up with these capping groups.